Swayam Prabha. Digital India. Educated India.
You all have heard of compressive strength, tensile strength of materials such as steel, wood, metals in general. Similarly, we have also compressive and tensile strengths for soils as well. But what is important in the case of soils from point of view of failure of soil under load, which is what is of interest in engineering, it is the shear strength that is of significance. Even when a soil is loaded under compression, then along some plane internally inside the soil may experience a shear stress which exceeds what may be considered as the capacity of the soil. In such a case, a slip or a slide takes place along that plane, and that in turn leads to failure of the soil. And therefore, there is a great need to understand what is shear strength of soils. Now, as we did in the earlier lectures, in this lecture as well, we shall ask ourselves a few pertinent simple questions and try to answer them. For example, to begin with, let us take a look at the first slide. The first slide shows three questions: what is shear strength, what is shear failure, why is it important? Let us take the first question. What is shear strength? As I said, that there will be an internal plane inside the soil mass along which shear stress may exceed the capacity to resist. So, shear strength is defined as the capacity to resist shear stress. The maximum capacity that a soil can mobilize in order to withstand without failure any applied shear stress along a plane is what is known as shear strength. Now, what is failure? In the case of shear, failure is by sliding or slipping along some plane. So, as I said, shear strength is therefore the resistance of a soil to shear failure, and shear failure itself results from an applied load, and it manifests itself in the form of sliding along some internal plane in the soil. Consider, for example, a cylindrical soil sample that is shown here. Suppose a load P is applied to this cylindrical soil sample, then this sample is likely to fail along a plane AB. The reason being, due to the applied force P, a stress tau is going to be mobilized or generated along the plane BA, and it will act downwards, and as a result of this, when there is a slip, there will be a resistance that will take place, and that resistance S, if that is equal to this tau, then balance is maintained and no slide takes place. But if the shear stress exceeds the shear strength S, then failure takes place. So, shear failure can be defined as that which occurs when tau is greater than S and it manifests itself in the form of sliding along any plane such as that shown here, plane AB. Now, shear failure occurs in different forms in different problems or different types of problems which we come across in soil mechanics. Take the example of a foundation. A typical shallow foundation will fail due to shear failure of the soil. So, at this point itself, let me make one clarification. I am going to talk about failure of the foundation, and when I say failure of the foundation, what I actually mean is the distress that is caused to the foundation due to shear failure of the soil. It is the soil which actually fails, but the distress is felt by the structure, and since the structure no longer is serviceable, we say the structure has failed and we say the failure of the structure, but actually what has caused it is the shear failure that occurs inside the soil. Take for example this typical foundation shown by these yellow lines. This is the position of the foundation when a load P is applied. Original position is shown in the form of these dotted green lines. So, when a load P is applied, the foundation is pushed into the soil. As a result of this, soil gets pushed out from below the foundation on both sides, and there will be a typical plane or surface of failure along which the shear stress exceeds the shear resistance, and this pushing out of the soil in turn will result in a heave on the surface of the soil. That means, any typical shear failure will involve sliding along an internal surface as shown here, as well as a result of that a slight heaving of the soil surface, and this is the mode in which a typical shallow foundation fails. There is another type of foundation failure. For example, suppose you have this foundation again represented by green dotted lines, initial position. Then when a load P is applied, if this load is not centric, if there is a rotation of the foundation, that rotation will also lead to failure, and once again there will be a shear surface of failure developing inside the soil, and correspondingly there will be a heave. Okay. So, this is the way in which foundations fail. There are also other structures like retaining walls, embankments. So, let us see how these fail. Here is an example of typical retaining wall failure. Suppose this white line, dotted line is the initial position of the retaining wall. Then when the soil fails due to shear, this retaining wall will take up a position like this. What really happens is, due to the pressure acting on the retaining wall from the soil, the retaining wall tends to move. If this movement is in the form of a rotation, then correspondingly at certain degree of rotation, after certain degree of rotation, a well defined plane of failure due to shear will develop inside the soil as shown in this dotted yellow line, shown by this dotted yellow line. This is again a form of shear failure. Let us take a look at an embankment slope. Here the typical surface of failure along which an embankment slope will fail is this red line. This red line is usually found to be an arc of a circle or very close to that, and you can see this soil surface after the slide has taken a new shape and position. This is the failed soil slope or the mass of soil that has slid. Now, this again is another form of failure. This again is due to shear. Now, the next question that we need to know or answer is, what is the importance of shear strength? Why is shear strength important? It is very simple. We do not want the structures to fail. If the structure is not to fail due to shear failure of the soil, then we need to understand what shear failure is all about, how is it caused, why is it caused, and then with that understanding we should be in a position to define or rather design a structure in such a way that it will not fail in such a way that it will give safe and satisfactory performance. So, understanding of the shear strength phenomenon, the phenomenon of shear failure of a soil is very essential. I am showing here now in this slide an example of shear failure of a slope. You can see this is nothing but a landslide, what we normally call as a landslide. This green line represents the original surface of the slope, and this yellow line shows the surface that is now visible after the slope has experienced a landslip. Next slide will show you in detail the original surface and the surface of failure, the surface along which the slope has slid and the surface which is now exposed as a scar. This is a typical shear failure, and it occurs because the soil mass that is contained between this failure plane and the original slope surface has a certain weight, say W. This weight has two components, one downward in the form of shear along this yellow line or yellow surface, and another an upward resistance in the form of S that resists this shear. We all know that whenever there is a slip between two objects or two surfaces, then friction is mobilized. So, this shear strength S that we are talking about, which has to be mobilized to resist this shear resistance tau, is nothing but frictional strength basically. But as you will see a little later, in the case of soils there is another component of strength as well, which is called cohesion. Let us proceed further. We shall now ask three more questions. These questions are: how do we determine shear strength? Because as I said, we need to understand what is shear failure if we want to design a safe and satisfactorily performing structure. So, we need to be able to determine the shear strength of a soil, so that we will be in a position to know whether the available strength at any point of time along any plane is sufficient to resist the shear stress that is going to be caused by any applied force. So, what are the factors on which this shear strength will depend is therefore also important, because once we know what the shear strength is under certain standard conditions, we can extrapolate and find out what the shear strength will be under different typical scenarios that exist in practice. For this purpose, we need to know what are all the factors which affect this shear strength and how they affect. And then lastly, naturally, we should know how to apply this knowledge in order to estimate and find out whether or not failure will take place and along which plane in a given situation, and then how to avoid that failure. Now, how do we determine shear strength? That is the first question. There are methods for determining the shear strength. Some methods are useful for the laboratory, some are useful in the field. We have seen earlier as well in the case of consolidation, when we discussed the chapter of consolidation and settlement, that it is very important to simulate the field conditions and therefore extract samples of soil from the field which are simulating the field conditions and test them under similar conditions in the laboratory as well. And the conditions under which the samples are tested in the laboratory should be as close as possible to the field conditions, and ideally it will be good to determine the shear strength in the field if possible, but alternatively it is good to extract samples and determine the shear strength in the laboratory under simulated conditions. There are many different methods for determining the shear strength of a soil sample in the laboratory, and some of these are also useful in the field. Let us take a look at a list of such commonly used methods for determining the shear strength. The commonly used methods for determining the shear strength are: 1. Direct shear test, DST for short; triaxial shear test, TST; unconfined compressive strength test, usually called as UCS or UCC. UCS standing for unconfined compressive strength, UCC standing for unconfined compression. Vane shear test is yet another test, the fourth one, which can also be used for determining the shear strength, and incidentally the last two are also useful for determining the shear strength in the field. Let us take a look at these tests in brief. Let me illustrate what we mean by direct shear test, triaxial shear test, and so on. In the direct shear test, what we do is to take a cylindrical soil sample. We shall see the dimensions, typical dimensions of this soil sample, and what length to diameter ratio it should satisfy, and so on, when we see some details of the test. In the sample, in the case of the direct shear test, this sample is usually like this, and we apply a normal load to this sample. This is the so called direct shear test. So, along some predefined plane, we will directly shear the sample by applying a load T. So, in this particular case, the applied load T will tend to shear the soil sample along this plane, say plane AB, which turns out to be a plane of failure, a plane of slip, nothing but the shear failure plane. And for different normal loads, if we can determine what is the value of T required, then we will be in a position at a later date to find out at what value of N and what value of T the soil has failed, so that we will know correspondingly what is the strength value at that time. The triaxial shear test, on the other hand, is considered to be a better test because it simulates the field situations, particularly with respect to stress conditions, more precisely, more faithfully. For example, suppose this is this cylindrical sample. You know, in nature, any typical element that is inside the soil medium will be experiencing not only stress from top and bottom, but also from the sides. There will be lateral stress as well, and it will also be acting perpendicular to the plane of this paper. Therefore, ideally speaking, if we want to test a soil sample under field conditions, we should be in a position to simulate this particular stress condition, which is essentially a three-dimensional stress condition. So, in a triaxial test, we apply stresses along three axes, and that is the reason why it is called a triaxial test. We apply initially, to begin with, loads on the sides, lateral pressure. After applying the lateral pressure, we apply normal or axial pressure and gradually increase this axial pressure until shear failure takes place along some typical internal plane of failure. This is the triaxial shear test. We also have a test known as the unconfined compressive strength test. In this, the difference is that the soil is not confined in the lateral direction. So, this is simply a cylindrical unconfined sample, no lateral pressure on the sides, and this is subjected to axial load until failure takes place along some typical weak plane inside the soil. And as in the case of the direct shear test, we try to find out what is the load T at failure, or here in this case what is the stress difference between the axial and the lateral stresses which is responsible for failure, and at the point of failure we estimate what is the shear stress which has caused the failure, and that happens to be also the strength of the soil. So, in unconfined compressive strength, you will find that failure takes place along this, and this is the shear stress that is mobilized due to the applied load, and at the time of failure, at the point of failure, the shear resistance should be equal to this tau, and therefore, the value of tau at failure happens to be the shear strength, and this is therefore the way we determine the shear strength of a soil. Take a soil sample, subject it to failure, determine the shear stress at failure. Shear stress at failure has to be equal to the shear strength of the soil. The Vane shear test is a slightly different test. It is also used in the field, although sometimes it can be applied also in the lab. It consists of a vane, a blade with a stem, and this vane is inserted into the soil and rotated. A torque is applied, and then failure takes place along a cylindrical shaped surface. We try to find out from incipient failure conditions what is the torque applied at failure. The torque applied must be equal to the total resistance mobilized, from which we estimate what is the shear strength of the soil. Now, the next question is, what are the factors on which shear strength depends? Although we will be seeing in very great detail each one of the factors and understand in what way they affect the shear strength, we shall at this point of time just say something about two major causes or factors. Now, for this we must understand what shear strength is composed of. There are two constituents which make up shear strength. One is friction, another is cohesion. Now, friction is a component that gets mobilized along the failure plane, and it is a function of the stress that is applied. So, friction depends upon the stress level. On the other hand, there is another component called cohesion, which is not dependent upon the stress level, but it depends upon the water content, and it is independent of the stress level. Therefore, shear strength has two factors or two components, which in turn are affected by several factors. As far as friction is concerned, the prime factor is stress level, and as far as cohesion is concerned, the most important factor is the water content or the amount of water, which in turn, as you will see, will be related to the rate at which water can flow out of the soil when shear failure takes place, that is, what is the drainage condition. Lastly, the sixth question is, where do we apply the knowledge of shear strength in practice? Knowledge of shear resistance is necessary for design of any structure in or on soil, for example, foundations, excavations, embankments, slopes, retaining structures, and all these structures ultimately fail by shear under certain applied loads, and it is necessary to understand how the shear failure takes place under each one of these cases, so that we will know how to design these for safe and satisfactory performance. Now, we have discussed the importance of the mobilization of shear strength to resist an applied shear stress. As a fallout, it comes out automatically that we now need essentially a method to determine the shear stress along any plane in a soil. If we have a method to compute the shear stress along any plane in a soil, we will be in a position to estimate the shear strength as well. So, let us spend some time to see how stresses are distributed inside a soil and how we can determine the shear stress on any potential failure plane. So, the remaining part of this lecture is going to be devoted to the stresses at a point and on a plane, stresses at a point and on a plane. Then, related to distribution of stresses and determination of shear stress, we also have a concept known as the Moore's circle concept, which is an integral part of understanding the distribution and determination of stresses at a point and a plane. So, we will also see this. Ultimately, after all, we are interested in failure. Therefore, we shall also take a look at what are the theories that are available to help us to estimate what the shear stress will be at failure, so that we will know what will be the possible shear strength that a soil can mobilize at failure. Now, this diagram shows how to estimate stress at a point and on a plane. This first diagram here shows a typical semi-infinite medium. P is a typical point inside the medium, and all these white straight lines here are nothing but different planes passing through this point P in the medium. Let us consider a horizontal plane, a vertical plane, and an arbitrarily inclined plane, the angle of inclination being theta with respect to the horizontal. Let us take an infinitesimally small element at this point enclosed by these planes. So, here we have the horizontal plane, here we have the vertical plane, and here we have the inclined plane at an angle theta. This we shall take as an infinitesimally small element, which will tend to be this point when the dimensions tend to become 0. For convenience of understanding the stresses and their distribution on this element, let us represent this in an enlarged manner as shown in this adjacent diagram. Here you will find that we have these 3 planes which make up the planes at this point, and on each one of these planes, as you know, in general there can be a normal stress and a shear stress. So, on a plane directed in the x direction, there will be a normal stress in the y direction. We will define now a set of positive stresses on each one of these planes according to a sign convention. For normal stresses, we will take compressive stresses to be positive and tensile stresses to be negative. Here sigma y is a compressive force, and therefore, the positive normal stress as far as sigma y is concerned will be 1, which is directed downwards. As far as sigma x is concerned, that is the stress in the x direction is concerned, the positive stress will be 1 that is directed from left to right, that is in the direction x, and acts on a plane y. The shear stress has a slightly more complex sign convention. Shear stress convention is defined like this: along positive or negative axis on a plane with negative or positive outward normal, the shear stress is positive. That is, suppose I take this plane x, the outward normal for this is directed in the negative y direction, and on a plane like this, a shear stress which is directed along the positive axis is positive, whereas on a plane y, the outward normal will be directed in the negative x direction, and the positive shear stress will be again 1, which is directed in the positive x direction, like this, in the positive y direction. So, the positive shear stress will be 1, which is directed in the positive y direction. With this, we shall now assume that the element has to be in equilibrium if the soil is not to fail, and then try to find out on any typical plane what is the shear stress and of course, what the normal stress is. So, as you can see, we are now converging on a method to determine shear stress on any plane. In the case of failure, this plane could be the failure plane. Now, how do we estimate the normal and the shear stress on any plane, any potential failure plane for that matter? What is known is the normal and shear stresses on the planes AB and BC, two mutually perpendicular planes, and what is required to maintain equilibrium is a knowledge of the normal and shear stresses on the plane AC. Suppose the length AC is capital L, then AB will be L cos theta, BC will be L sin theta, and assuming all these stresses to be distributed uniformly, and this assumption is not an error because the element is an infinitesimally small element, and therefore, on these small lengths AB, BC, AC, it is perfectly reasonable to assume all the stresses to be uniformly distributed, in which case the force on plane AC, for example, in the normal direction would be sigma into L. Similarly, the shear force will be tau into L, and identically the forces on the plane AB will be sigma y into L cos theta and tau ix into L cos theta, and similarly here. And now we can write down an equation for equilibrium of all these forces. The equations of equilibrium can be represented in terms of sum of all the forces in the sigma direction equal to 0, which will give us an expression for sigma like this, and sum of all the forces in the mutually perpendicular tau direction equal to 0, which in turn will give us an expression for tau like this. So, sigma is expressed here in terms of the known stresses on two mutually perpendicular planes. Similarly, tau is also expressed in terms of stresses which are known on two mutually perpendicular planes. So, here we have the two expressions which are very useful in determining the normal and shear stresses on any arbitrary plane if we know the stresses on two mutually perpendicular planes. Now, let us take this normal stress in particular. If we want to find out where this normal stress will be maximum or minimum, we need to simply differentiate it with respect to theta. What is d sigma by d theta? It will be equal to this, and when you simplify this, you will find that it works out to an expression which is nothing but 2 times the expression which we have seen in the previous slide for tau. So, when sigma is maximum or minimum, shear stress tau is 0, and this happens at a particular value of theta, and the planes AB and BC at that value of theta will have only normal stresses on them and no shear stress, and one of the normal stresses will be the major principal stress sigma 1, and the other one will be known as the minor principal stress sigma 3, and any normal stress on a plane on which there is no shear stress is known as the principal stress, and these principal stresses can be obtained if we know what is the value of theta at which d sigma by d theta becomes 0, and substituting that value of theta, we can show that sigma is equal to this and tau is equal to this in terms of the principal stresses sigma 1, sigma 3. So, this sigma and this tau can be also expressed in terms of sigma 1 and sigma 3, unlike in the previous slide we expressed them in terms of sigma x tau xy and sigma y tau ix. These two expressions are extremely convenient for graphical representation and understanding of the process of failure. The principal stresses in a typical 3-dimensional case are 3 in number, sigma 1, sigma 2, sigma 3. We shall, however, simplify this problem and consider a planar 2-dimensional problem and deal with only the major principal stress sigma 1 and the minor principal stress sigma 3. Now, we will see what is known as a Morse circle. We have just now seen that the shear stress, normal stress and the shear stress can be expressed like this in terms of the principal stresses. These two expressions suggested to Moore that it is possible to draw a circle in such a way that the radius of that will be nothing but sigma 1 minus sigma 3 by 2. If you draw a circle with one end at sigma 3, another end at sigma 1 and radius as sigma 1 minus sigma 3 by 2, and now from this point B, if you draw a line parallel to the side of the infinitesimally small element, then you find that this B A represents one of the sides, the side on which sigma 1 acts, and A C represents the inclined plane at an angle theta along which we want the stresses. Then the point C has coordinates sigma and tau, which are given by these two expressions. So, here we have a method where if we know sigma 3 and sigma 1 and plot them in the form of a circle as shown here, and then plot the infinitesimally small element, particularly the plane along which we want the normal and shear stress, then we get the point C whose coordinates are sigma and tau, which are nothing but the normal and shear stresses of the plane of interest. Now, in the case, special case, where this plane sigma 1 major principal plane is horizontal, this diagram will slightly simplify and angle theta will be this. And once again the point C will have coordinates sigma and tau given by the same two expressions, and this line OC will have an expression given by root of sigma square plus tau square, because this is sigma and this is tau, and therefore this length represents root of sigma square plus tau square, and this point A is known as the origin of planes. Now, our prime interest in plotting this Morse circle of stress is to find out what is that plane AC whose orientation is such that the corresponding shear stress causes failure. Idea is, once we have a method to find out sigma and tau, we want to find out what is that plane where tau causes failure, because if we know that plane at which tau causes failure, that would mean that that is the plane along which the shear stress is just equal to the shear strength. So, we can determine the plane of failure and correspondingly we can determine the shear stress, and that is nothing but the shear strength of the soil. So, the Morse circle of stress tells us a method or gives us a method to check whether or not failure will occur along a plane inside the soil, and that is what we are basically interested in. Now, if there is a plane of failure, then the angle theta for that plane of failure will be given by 45 degrees plus phi by 2. Let us take a look at the diagram once again. See, this value of sigma and this value of tau give rise to a point C. Corresponding to this point C, is possible to draw a tangent, and this angle, let us say, is phi. You can see here that this is a limiting value of this angle phi, which is known as the angle of obliquity, and it can be shown that it is this angle phi, limiting angle phi, which represents failure, which is a measure of the failure, and therefore corresponding to this point C, the plane, inclined plane, will be having an angle which is the critical angle corresponding to the state of failure, and tau is the shear stress corresponding to the plane which is at an angle theta critical. Now, if this angle is phi, it is obvious that theta critical will be nothing but 45 degrees plus phi by 2, and it also is obvious that the shear stress tau will be related to phi by an expression that tau is equal to sigma tan phi. This shear stress tau is sigma tan phi, and therefore, at failure we can say that the shear strength of the soil is nothing but sigma tan phi, and that is the basis of a number of theories which have emerged subsequently on the concept of failure. So, once we know theta critical, correspondingly we can write down some more expressions, one for sin phi, another for the ratio of sigma 1 and sigma 3 in terms of sin phi. So, these two expressions are actually similar. Here sin phi is expressed in terms of sigma 1 sigma 3, here sigma 1 sigma 3 are expressed in terms of sin phi. So, these basic expressions will help us to find out what is the plane of failure and what is the angle of obliquity at that point phi, which defines the potential failure plane. Now, there are many theories of failure. Basically, we shall be seeing three theories of failure. One is the Moore's failure theory. We call it the Moore's strength theory, because after all failure corresponds to the state at which the strength is fully mobilized. So, the failure theory also can be referred to as the strength theory. We have a strength theory known as Moore's strength theory. There is another theory which also we shall see, which is known as the Coulomb's strength theory, and then we shall also see a Moore's general strength theory. Let us take a look at these three theories. The Moore's theory starts with the assumption that the intermediate principal stress has no effect on the strength, and no variables other than the stress have any bearing on the shearing strength. That means, in effect, the concept of cohesion simply is not included in this, as we have seen earlier itself that friction is a component of strength which is dependent on the stress level. So, this theory indirectly is stating that strength is dependent on the friction, and as per this theory, failure will occur on a plane on which shear stress is related to the angle of obliquity phi in terms of tau is equal to sigma tan phi, and this can be expressed in terms of a Moore envelope. Here in fact, I have 4 envelopes, and we know that at failure this green line where it touches the Moore's circle defines the point at which tau will be equal to sigma tan phi. So, that is the point which represents the stress state on the failure plane, and if you join this with D, you get the failure plane. Now, consider this first Moore circle, number 1. This Moore circle touches this green line, which represents a line with an equation tau equal to sigma tan phi. So, this is referred to as the strength envelope, and since this theory is that of Moore, this is referred to as the Moore's strength envelope. So, if this represents the strength, limiting strength, then the first circle has stresses sigma 1 sigma 3 in such a way that it just touches this, and this represents a state of stress which corresponds to failure. On the other hand, if you take the circle number 2, this does not touch the envelope. That means, although the shear stress here is equal to this shear stress, the sigma 1 and sigma 3 values are such that this circle does not touch the envelope, and therefore, this stress state does not correspond to failure. On the other hand, the larger envelope, the larger Moore circle 3 again corresponds to a state of failure because it touches this, whereas the circle 4 again represents a state of no failure. So, Moore's envelope can be taken as a guideline for checking whether any stress state defined by the Moore circle corresponds to failure stress state or not, and that is what the Moore strength theory is all about. According to Moore strength theory, shear strength is tau equal to sigma tan phi, and by plotting the Moore circle and the Moore's envelope, it is possible to find out whether or not given the given stress state corresponds to failure or not. And if it corresponds to failure, then we can calculate phi theta critical from these expressions. Now, there is the second theory, the Coulomb strength theory. This theory is an empirical theory first of all, and according to this, the sliding force on a solid mass is F is equal to C plus n tan phi. Now, this is something which you know already from physics. Coulomb's law of friction is known to you already from physics. If there is a body which is sliding on a plane, if there is a normal force N, you know that the force F that is required to shear this will be equal to n tan phi plus some component which is independent of n. So, that is what Coulomb says, that the force F that is required to cause instability sliding will be having two components, one is proportional to n, another is independent of n. The component which is proportional to n will be given by n into tan phi, where this tan phi stands for the well known coefficient of friction. In this case, the sliding takes place inside the soil along some plane, and therefore, this coefficient of friction corresponds to the friction coefficient along some internal plane of failure inside the soil, and so this is very often referred to as the angle of internal friction. Internal friction. But nowadays, it is more frequently referred to as the angle of shearing resistance, because it is this angle which goes into computing the strength, that is, this defines what the strength is. So, this is known as the angle of shearing resistance. This is the Coulomb's theory, where C is a constant value, N is the normal force, F is the force required to introduce sliding, and phi is the angle of friction between the surfaces of sliding inside soil. Now, this can be applied to soil, and if we take a finite area of contact A, then all the forces can be converted into corresponding stresses, and we can say that the force required to fail is nothing but the strength, that is S, is equal to small c, which is equal to nothing but capital C by A, plus n upon A, that is sigma, into tan phi. These parameters C and phi which go into this equation are known as the shear strength parameters. So, this means that if in any situation, if I know the normal stress on a plane, and if I know the cohesion and coefficient of friction phi, then I will be in a position to calculate the shear strength S using Coulomb's failure theory. And incidentally, this equation is a purely empirical equation, but practice has shown that it is widely applicable and quite reliable, and therefore, even today, in order to evaluate the strength of a soil, we use the empirical equation of Coulomb. This third theory is nothing but a generalized form of the Morse strength theory. Here we say that the shear strength is not just sigma tan phi, we say it is some function of sigma n. It need not be sigma tan phi, it could be some other, in fact even nonlinear function of the normal stress sigma. So, if we were to plot the Morse circle for this general theory, you will find that there will be a Morse circle corresponding to which there will be an yellow envelope like this, which in the most general case will not be now a straight line, and it would also pass like this, so that this will become an envelope even for stresses representing tension. So, the Morse general strength theory is applicable to both compression and tension, and the envelope that we get covers from tensile to compressive zones, and this point as before is the point corresponding to failure, and this is the point for which the shear stress is equal to the shear strength S given by F sigma n. And what is this F sigma n? Once again, practice has shown that S is equal to C plus sigma tan phi is sufficiently representative of this function of sigma n. And once again, therefore, we will reinforce the statement that if we know C and phi, the shear strength parameter, and if we know the normal stress on a certain plane, we can determine whether or not that plane is a plane of failure, because we can get the shearing strength from this C, sigma and phi. We can calculate the shear stress from equilibrium considerations. If the shear stress exceeds the strength, then there will be failure, otherwise not. As I said, there are two components contributing to shear strength. One is friction, another is cohesion. And if we take a typical soil sample, apply a normal load n on a plane of failure and apply a shear stress tau, as we saw some time back in the case of the direct shear test, then this T will be a function of the normal load if this material is a frictional material, that is materials like sand, gravel, coarse grained materials. If on the other hand we have fine grained materials like clays, then there will be a component contributing to T which is going to be independent of this normal load n. Of course, the component proportional to normal load n will be there, but in addition there will also be a component which is independent, which is what is known as the cohesion component. In general, there can be soils which are having purely only cohesion, there can be soils which are purely frictional, and real soils lie between these two extremes, and most real soils have both cohesion and frictional component. Now, let us see a quick example of how to use this Morse circle. This example says that if we know sigma 1 and sigma 3, how do we calculate the stress on a plane inclined at 45 degrees to this sigma 1 major principal plane, and also we find out what is the maximum shear stress. So, this is the Morse circle. Where does the maximum shear stress occur? Obviously, the maximum shear stress occurs here, just above the center of the circle, the shear stress, whereas at failure the shear stress is only this much. Therefore, maximum shear stress need not necessarily mean failure. On the other hand, failure there depends not just on the shear stress, but on the ratio of tau to sigma, and when that ratio, which is equal to C plus sigma tan phi, is satisfied, that only will correspond to the state of failure. Now, we have been given in this example sigma 1 and sigma 3, the stress corresponding to point B and stress corresponding to point A, and value of theta is 45 degrees. So, we need to find out what is the shear stress. Let us see, the solution is on a plane at 45 degrees, if we use these two expressions for normal stress and shear stress in terms of sigma 1 and sigma 3 and put the values of sigma 1, sigma 3 and theta equal to 45, then we simply get sigma equal to 300 and tau equal to 200. And incidentally, it so happens that this plane of 45 degrees, if you see the Morse circle again, is nothing but a plane which passes through this point here. That means, the shear stress on this plane is nothing but tau max. So, this shear stress tau incidentally corresponds to the maximum shear stress as well, which was asked in the example. So, tau max occurs when theta equal to 45 degrees, and here since the given plane is at 45 degrees, it is also the plane of maximum shear stress. And what is this maximum shear stress? The maximum shear stress has to be the shear stress which we have just now estimated, and that is 200, and the corresponding normal stress on that plane will be 300. And so, from the Morse circle given sigma 1 and sigma 3, we can always determine the normal and shear stress on any plane, and then find out whether or not that plane is a failure plane by applying one of the failure theories. We determine tau we determine sigma. If tau satisfies any one of the failure theories, then we know that that corresponds to the state of failure. So, in this lecture we have seen concepts of Mohr circle, some failure theories. We have also seen an example of how to use Mohr circle and we have seen what are the tests which are available for determining shear strength. In the next lecture, we will see some details of the various shear strength tests and their corresponding Mohr circles. We will also see what are the factors affecting shear strength and how they affect, and then we will see some applications of these in the form of some examples. Thank you.